Hi everyone. This is a video to explain Word2Vec from a conceptual perspective. So Word2Vec is a two-layer neural network that was introduced in 2013 by Mikolov et al. Word2Vec generates vector representation or what we call as embeddings that capture the semantic and syntactic properties of words in a corpus. It's a much simpler model to understand compared to, say, transformers, which is driving the current state of art in NLP. And Word2Vec consists of two algorithms, continuous bag of words and skipgram. And in this video, we will be focusing on continuous bag of words. Now, this is what a typical architecture of Word2Vec looks like. It has the input layer, the hidden layer, and the output layer. The input layer is a one-hot representation, which essentially means that the vector length is as long as many words in the vocabulary. So if you have a vocabulary of size 10,000, then the vector length is 10,000. And for a given word, let's say the word is x sub k, the value of that corresponding vector is 1, and the value for the remaining uh, vector position is 0. The hidden layer consists of a vector of size n. N can be anywhere from 100 to 300 or 350. And the last layer is an output layer, which is again the same size as the input layer. So as many words in the vocabulary, that many elements in the output layer. So how does the training happen in Word2Vec? So let's consider a paragraph. So this is the Wikipedia entry for Word2Vec, the first few sentences. We pre-process the text to generate something which is shown below. We get rid of the stop words, the punctuations, and we start with essentially a window of 5 words, and the window size can vary based on your training requirements. So in this, the window size is 5, where we consider 5 words, and the middle word uh, is the target word, and the remaining words to the left and to the right are the context words. So what you're looking at is the continuous bag of word algorithm of Word2Vec. Now, after one iteration of this training window, the training window slides to the next word. Now here language becomes the target word, and the context words are technique, natural processing, and NLP. And you slide this window across all the words in the corpus, and for each window you have one iteration of the training algorithm. Okay, this diagram represents the training cycle in Word2Vec. So what you're starting with is essentially the vocabulary matrix, which is nothing but, say, if the vocabulary size is 10,000, you have 10,000 vectors, and each vector represents one word in the vocabulary. So this is a matrix of size 10k into, say, the vector size can be, let's say, is 100. The next is the sentence words. So this is one sliding window where your target word is this here, word 5, and the remaining words, word 1 to word 4, word 6 to word 8, word 9, sorry. These are the context words. Now when you come to this column here, context word embedding, they are the vector representation for the corresponding words from the vocabulary. So you're essentially pulling in the vector representation of word 1, which is embedding 1, word 2, embedding 2, so on and so forth, up to word 9. But you do not include the vector representation of word 5 because that is what you're trying to predict. Now, you aggregate these context word embeddings to generate the aggregated context embedding. So this can be either the sum or this can be an average, the mean. So for this example, let's consider the average. And once you have this contextual representation, you essentially have a vector representing the context in which word 5 occurs. Now you have another set of vectors, again of size 10k cross 100. Now this represents the context representation or the context vector for each of the corresponding words. All right. And what you're doing is essentially taking the contextual representation of word 5, this is embed C, and then having an inner product with each of the vectors in the context embedding. And your goal is to get a very high score, a very high inner product for what you're trying to predict. Uh, Once you have this scalar value, which is the inner product, then you pass this through softmax. And you get a probability score for each of the representation, each of the words in the vocabulary. And your goal is to have a very high representation for the corresponding word you're trying to predict. Now, once you have the probability score, you also have the true label. So this is part of training. So you have the labels available with you. You sort of take the difference and you back propagate. You update the corresponding vector representation. Let me change my color. So you have an update to all the vector representation based on your back propagation delta. Now you back propagate further, you have an update to the aggregate context embedding. And when you back propagate again, you have an update to the vector representation of each of the words which represents, or each of the vectors which represents word 1, word 2, word 3, word 4, word 6 to word 9. So you're essentially updating uh, two matrices. This is a matrix which has the context embeddings, and this is the matrix which has the word embedding. All right. So once again, predict the probability score, look at the true score, uh, back propagate, update the context embeddings, update the aggregate embedding, and then you update the individual word embedding. Okay, so far we have seen how the vectors are updated, specifically two sets of vectors. One is the word representation and the second one is the context representation. Now let me erase this. Now let's consider, say, a context as, now let's consider an apparel context. So things like shirt, say pants, jeans, jacket, so let's say these are words you typically consider in the context of an apparel. fashion, clothing. Um, and let's say we think of the word something like wore, that's an R, W-O-R-E, or W-E-A-R, where. Now, you can have any of these context word occurring with, say, one of these target words. So if you're trying to predict the context of war, so for example, if war is the word 5 here, so you go all the way up to the context representation of war, and you update the context embedding, but you also update the individual vectors, the contextual vectors of the word war. All right. Now, when you update them, you want these updates to help you predict the context word of war better. So, as the training happens, as you um, see more contexts in which war is the target word, and say some of these words occur in the context, and when you update them, the vector representation of these words would start not looking same, but they will start occupying the same region in the vector space. So the training algorithm moves them or updates them in such a way so that it helps generate the correct context representation for war, and which helps in aligning with the context representation of the word war in this matrix. Similarly, for where or any other word which typically would co-occur with apparels. I hope this makes intuitive sense. So when you update these vector representations of shirt, pant, jeans, jacket, which occurs in the context of the word wore or wear, so you are essentially updating these vectors here. You would update them in such a way that their values would, the vector representation of these words would come closer together. Okay, and that's essentially what Word2Vec does. It essentially looks at the context in which these words co-occur. So if they share a similar context, then they start getting values, similar vector representations. Now let's look at another example. Now let's say instead of uh, shirt, I only have pant or pants and jeans. So these are, you wear them for your legs, and then you have, what can be the context? Let's say you have a word something like waist, W-A-I-S-T. Maybe waist size, something like that. Yeah, this is a good word, so I can explain something else also. So when you're looking at the contextual representation of waist, you typically see something like pants and jeans. And when you do the vector updates in here for the corresponding contextual vectors for waist, you sort of update the vector representation of pants and jeans, and they start having similar values. All right. Yeah, so typically you would see when you see waist, or so when you say pants, you might see waist occur with it. When you say jeans, you would see waist occur with it. And maybe we are looking at so the retail domain where you're describing these items, and you say something like waist size of jeans, waist size of pants, and these vectors start moving towards the same vector representation. Uh, but what happens, let's say you have waist size. So size is also a contextual word which occurs with waist and jeans and pants. But now what happens is, um, while waist is can be more strongly associated with pants and jeans, size need not be strongly associated with waist alone, because size can also occur with I don't know, shirt size, maybe shoulder. So size, um, the vector representation of size is influenced, of course, influenced by the context representation of waist. But since it occurs in other contexts like shoulder size or shirt size, it also gets influenced by the vector representation, or sorry, the context representation of shoulder and size. So you want to update the vectors representation of size to help you predict the context of shoulder, shirt, and not just waist. So what would happen is, while pant and jeans, so this can also be only pant, only jeans, or yeah. So while these two vectors typically have a much stronger association with waist, so they start moving closer to each other. The vector representation of size, although it also occurs with waist very often, but it also occurs in other contexts as well. So one set of training would try to move them, say, closer to jeans and pants. Another set of training context would move the vector representation of size closer to shirt or shoulder. So it's not a given that size would have a closer representation to jeans or pants, but it's very likely that pants and jeans would have much closer representation to each other. So this is how Word2Vec updates the vector representation of words and brings words that occur in the same context closer to one another. Okay, let's consider one more example. Let's look at the word size, and let's say we have screen 6 inches. This is another word, 6.5, maybe 5.7. And let's look at something, another context as shirt. XL, L, M. Yeah. Okay, now size appears in two contexts, one related to apparels and one related to smartphones. Now, um, so if you're looking at a context where you have shirt size and say XL, you can have size, and since this is a sliding window, in some instance size is the target word, in some instance XL is the target word, and in some instance shirt is the target word. So whenever shirt is the target word, you have updates. Excel gets updated to help predict shirt, the context representation of shirt, and the vector representation of size is also updated to help predict the context representation of shirt. Similarly, L gets updated to predict the context representation of shirt, and so does M. Now, these sort of updates, they would pull these set of words in one specific direction. And similarly on this side, if screen is the target word, then 6" would be updated to help predict screen. 6.5" would be updated such that it can predict screen, and so on. And in both the cases, size also gets updated, but in some cases, size gets pulled towards this, and in some instance, the size gets pulled towards this. So in a way, uh, if say size C is in the corpus, there's a lot of occurrence of size with respect to shirt XL in the first part of the training data, and maybe your vector representation of size is more aligned with size XLL and M. But in the second part of the training data, it starts seeing size screen 6", 6.5". Then this vector representation gets undone and it sort of goes in the other direction. I mean, this is not literally how it happens, but I'm sort of trying to give you an intuitive sense of what could happen. Uh, it's likely that you see more examples of shirt XL. Say, if this is a catalog and you have more apparel examples than smartphones, then the word size could get more strongly associated with apparel terms and less so with the smartphones. So how these vector representation pan out depend a lot on what is contained in the data. So hopefully that gave you an understanding, a conceptual understanding of how Word2Vec works, specifically how the training happens in Word2Vec and how the word vectors and the contextual vectors are updated.